Here we focus on the biharmonic problem and how to find a way to derive the variational form of the biharmonic equation. The biharmonic equation is of this form. This is the biharmonic operator here. So is the operator acting on the function u equals minus f in the domain omega plus some boundary conditions specified on this bounded region omega. U is a minimizer of this functional, and we will use this functional to derive the weak formulation of this problem, the biharmonic equation. First of all, we find this perturbation u plus epsilon phi. We use this perturbation here in our functional. So how can we write this? The Laplacian operator is a linear second order operator, so we will have Laplacian of u plus epsilon Laplacian of phi squared minus this integral f, and here we have this perturbation u plus epsilon phi. We do some computations here. We split this integral here, f times u minus epsilon integral of f times phi d omega. We split these integrals here. Minus the integral over omega phi times u d omega minus epsilon integral over omega phi times phi p d omega. Now we can write this in the following way. W, the functional of u plus epsilon phi, equals W of u. If you notice here in the previous page, this one and this one together give me this functional W. So I substitute to make a little bit the relationship more elegant, and then I end up having three terms. Have the integral over omega Laplacian of u Laplacian of phi d omega minus the integral over omega this is the function phi f times phi d omega plus 1 divided by 2 epsilon squared integral over omega Laplacian of phi squared. Now what I can do from here, I take this difference of the functionals here, minus W of u equals epsilon, and here I have the integral of the Laplacians of u and phi plus epsilon squared divided by 2, the integral of Laplacian phi squared d omega. Now I take the limit as epsilon goes to 0 of this difference here of the functionals minus W of U divided by epsilon. Basically, is the limit. In the numerator, I have this, and I divide by epsilon and take a limit of epsilon going to 0, which means that this term vanishes, and I only have this term here, integral over omega, grad Laplacian u Laplacian phi d omega minus the integral over omega f times phi d omega equals Laplacian of u Laplacian of phi d omega minus the integral over omega f times phi d omega. And I take that equal to 0. From here, I have that the integral of Laplacian of u Laplacian phi d omega equals the integral over omega f times phi d omega. The integral over omega Laplacian of u Laplacian of phi d omega equals the integral over omega f times phi d omega. This is the variational form of the biharmonic problem. Now let's define the space for u and phi. U belongs to h0, 2 of omega. Phi is the test function, belongs to h0, 2 of omega. And f belongs to the space of square integrable functions. What is this h0, 2 of omega? So is w. Such that the integral over omega w squared d omega. So this norm, L2 norm is finite. Then the gradient of w, the norm of the gradient in L2 is finite. And also the norm of the Laplacian is finite. And that the function becomes 0 at the boundary of omega. And L2 space is the space of square integrable functions. So it's psi from omega to r, such that the L2 norm, this psi squared d omega, is bounded. You can derive, I have prepared the previous video that is available for the Laplace problem. When you have the Dirichlet functional, you can obtain the weak form, but here instead of the Laplacian operator, you have just the gradient of u times gradient of the test function. Here I have the Laplacian of u, Laplacian of phi. And at the right hand side, I just have this linear functional of f, the integral over omega of the function f times phi.